great pleasure to introduce Nigel, who will tell us about nodal curves.
Okay, well, thanks very much. Well, it's true that I've been an enthusiast for twistor theory for nearly 50 years. I learned about it, when I was a postdoc in Oxford in the mid-70s, and I've used it in all sorts of mathematics ever since. But for virtually all of those occasions when I've used it, in hyperkähler geometry or self-duality, a twisted line has been a smooth, rational curve. That your twistor theory involves looking at families of classical twistor theory, families of smooth, rational curves in some complex manifold. And that family has some induced differential geometry on it. So what I'm going to be talking about today is where you replace the smooth rational curve by a nodal one. And this is something which has been around for a few years now, mainly through the work of Honda and his collaborators. And it's something which I kind of knew about in the background but never took much notice of. But I found myself face to face with it when I was trying to understand, trying to revert to an old problem which bothered me, which was looking at the twistor approach to finding an ALE metric, an asymptotically locally Euclidean metric. So you'll find out later what I mean, but it was then I began to appreciate that you can study nodal curves with ordinary singularities in the same way that you can do for smooth rational curves. So let me begin just with refresh your memory. So the original twistor theory for, if you like, the nonlinear graviton is where we have a complex three-manifold and we have rational curves inside it whose normal bundle is the direct sum of line bundles O1 plus O1. And on the space of such curves, so there's a four-dimensional space of such curves, and there's a self-dual conformal structure on it. And the conformal structure is defined by saying that 2 points in the four-manifold are null separated if the 2 lines, or the 2 twistor lines that they correspond to, actually intersect. So null separation corresponds to the intersection of these 2 curves in a three-dimensional manifold. So now, suppose we have a free holomorphic action of C star, or even the additive group C, and we take a twistor line which is transverse to this action. Then a neighborhood of that line, you have a quotient of a neighborhood of that line, which maps to the quotient space as an orbit space, which is now two-dimensional. It's a surface S, and the normal bundle of the curve has inside it now the tangent vector of the action, which is a trivial subbundle, and the quotient is now a line bundle of degree 2. So the image of the curve in this surface has normal bundle O2. And so now you can look at this from the point of view of twistor theory and say, suppose we have a complex surface, a complex two-manifold, and we have rational curves, self-intersection 2, or whose normal bundle is O2, then the space of such curves is three-dimensional, and it has an induced structure, an Einstein-Weil structure. So this is a conformal, a torsion-free connection preserving the conformal structure so that the symmetrized Ricci tensor is a scalar. So I wrote about these in the early 80s, mainly from the holomorphic point of view. But there's this feature here. Noticed at the time that if actually S is a compact surface, if it's an open set in a compact surface, then the Einstein-Weil structure you get is a constant curvature metric. So this imposes some limits on, you might say, okay, we can look for all sorts of three-dimensional twistor spaces, construct them in different ways, and find different self-dual conformal structures this way. But if we're trying to construct a compact surface and do it, then we're bound to get either flat space or hyperbolic space, or depending on the signature, or the spherical metric. So what goes wrong? Well, here's one way of looking at it. So let's suppose we have the C star action. And suppose we have 2 points on an orbit. So x in M, in this 4 manifold, and lambda x. So these are 2 points on the orbit. And then if they're null separated, then we have a point, a non-trivial point on the intersection of the curve C, Cx, and its transform by lambda. So in other words, we have 2 points, y and lambda inverse y, which lie on the same orbit. So if we now look at the projection onto the orbit space, then we have a rational curve. We have 2 points in the same orbit, so the projection, they get identified. And so the image is going to have a singularity, a node where these 2 points become identified. So that's the reason. I mean, there's a. And now you might wonder, so is this compatible with what I wrote about all those years ago? And the fact is that, well, first of all, we have this. So this is really a theorem. So Honda's written several papers, but this particular one includes this particular theorem, which says that if we now have a smooth projective surface, so compact surface, if there's a rational curve C which has a certain number of nodes, that's just ordinary singularities, and if, as all its singularities, so we don't ask for any cusps or any more complicated singularities, and if this number here, the self-intersection number plus 1 minus 2 delta is greater than 0, then the variety of such curves is non-singular and has this dimension. So this is it has a theorem which is a deformation theorem, in the same way that in classical twistor theory we have Kodaira deformation theory about curves in higher dimensional manifolds. Then there's a version of that which he does, and so this is a general statement. And so if we're interested in the quotient of a twistor space, a three-dimensional twistor space, by the action of C star, then we want a three-dimensional space of curves. So that means asking for C squared plus 1 minus 2 delta be equal to 3. That's equivalent to saying that the intersection number of the canonical divisor with C is equal to minus 4. So an example of this would be if you have a quadric surface and a smooth plane section. So that's not of course, that's a smooth version of this. So a plane section of a quadric surface, this is the mini twistor space that gives you hyperbolic space. Then that's if you like the smooth model. But here we're allowing nodes, and then so the key point about it is that we want Kc to be equal to minus 4. So we want rational curves which have nodes and such that Kc is minus 4. And what Honda and Nakata show is that actually you can, if you have one of these curves, C, then you can normalize the neighborhood of it in such a way that the normalization of the curve is a smooth rational curve and has self-intersection number 2. So this is compatible, if you like, with the previous version in the sense that a small neighborhood of a rational curve how should I put it? That a small neighborhood of one of these nodal curves, actually the geometry is the same, the local geometry is the same as taking the normalization and looking at the standard version of mini twistor spaces. Okay, so I'm interested. So ultimately, I'm interested in applying these ideas to ALE spaces, which are hyperkähler. So, but let's think about how this picture works in the hyperkähler case. And so, for a hyperkähler manifold, so then Z might be is of higher dimension. So this is, or it might be three-dimensional. I mean, in fact, I'm only interested here in three-dimensional case. That in this case, the twistor space fibers over the projective line, and the twistor lines are sections of this. So there are different types of actions that you might have, and there's the triholomorphic action, which is where the C star actually preserves each fiber of this vibration. So it acts trivially on the base, on P1. And that's equivalent to saying that in terms of the geometry of the hyperkähler manifold, that it acts trivially, it preserves all three symplectic two forms. So now in this case, since a twistor line is a section, and then it intersects a fiber in just one point, but the C star action is along the fiber, so that we don't get any 2 points in the orbit which are null separated. So in this case, you don't get any 2 points which are going to go to the same point under the projection. So in this case, you actually get a curve in the quotient, which is an open set in the total space of O2 over P1. And this, if you like, this is basically the Einstein-Waal structure here is, well, C3, but I'm working over the complex numbers without putting the real structure in here. So it's C3, and so this is essentially the Gibbons-Hawking ansatz. That if you have a triholomorphic vector field, then you have a particular ansatz in which involves a solution to Laplace's equation on R3. So that's the kind of the simple version of a C star action. The other alternative action is if you have an action where one of the hyperkähler forms is fixed and the other two are basically rotated. So in this case, the C star action acts non-trivially on the projective line. It has fixed points at U 0, where so U is my parameter, it's an affine parameter on the projective line here. At U equals 0 and U equals infinity, then you have a complex structure which is preserved by this C star action. So in that case, where are we? In that case, where are we? Oh, I've gone back. I've got to go back. I pressed the wrong button there, sorry.
No, you did go. I want you to go back.
Was there a question?
It sounds like there's a question on Zoom.
Ah. Okay. Is there a question?
I'm not sure.
All right.
You should be able to see the participants on Zoom on your laptop.
Oh, should I? Oh, should I have that? Sorry.
I'm chairing tomorrow morning session, so I'm going to watch it.
Oh, sorry. I didn't realise this was part of the...
Okay, so where were we? This is the alternative action. So what I'm going to say is that omega 1 is a fixed 2 form, and the corresponding complex structure, I or minus I, corresponding to plus or minus omega 1, these are complex structures which are fixed by this C star action. So, but the point is here that the action is the standard action on P1, and the action is transverse to the fiber over, let's say U equals 1. 1 is just a convenient number. So here the idea is this, that can we, in order to try and understand the quotient by this C star action, maybe we could take the inverse image of the fiber over 1 as being like a slice for the action. And then maybe we can find our nodal curves inside this surface S. Maybe we can make S into a mini twistor space in this nodal picture of Honda. And now there are problems with that. So first of all is that, well, certainly in the cases we're looking at, the inverse image is one is non-compact, and more importantly, perhaps, that the C star orbit, although CX twistor line is compact, C star orbit won't be. I mean, there'll be limit points which are not on that orbit. And also, more significantly perhaps, is that if we look at a point on the fibre over 0, then that whole fibre is preserved by this C-star action, so that no point on that orbit will ever intersect this slice. So, so what can you try and do? What we need, and so this restricts the possibilities you can look at. We need to look at the closure of the orbit, and we need to see that inside a compactification of this inverse image. So we're looking here, we have to look at things which are essentially algebraic in order to put this into effect. And what is the standard example of this? Well, the standard twistor space for flat space is the total space of O1 plus O1 over P1, and we can compactify that in the way that Roger originally did it. I mean, looking at P3, looking at lines in P3, these are the twistor lines in this particular case. So let me show you, this is more like an exercise, show you what can happen and what can go wrong if we try and do this here. And then later on, you'll see that hopefully that when we do it in the ALE case, then we find that things work much better. So okay, so now let's look at quotients of flat space. So now I want to take this action. So one for each n. So this is an action where the action on dz1 wedge dz2 is e to the I theta. Okay, so I'm fixing the action here on the holomorphic 2 form as being multiplying by e to the I theta. So there are different values of n for which you can do this. And then the corresponding action on the twistor space looks like this. The twistor lines, in this case, are just given by these, the 4-parameter family of twistor lines, A, B, C, D. And if we want to project onto u equals 1, it's equivalent to eliminating lambda from these two equations. So before we do that, just note that we've got to consider the closure, so we've got to consider limits. So as lambda tends to 0 or infinity, this curve intersects the line at infinity in P2 in 2 points. So, okay, so if we do n equals 0, say, then we've eliminated lambda. So, okay, so where were we? Yeah. Oh, wrong one. So n equals 0 is just the action. Where are we? This is. That's right. So n equals 0 is where z1 is fixed and z2 is multiplied by e to the I theta. So in that case, the closure of the orbit is obtained. Well, this is what we obtain just by eliminating that parameter lambda. And what you see is that you have a conic. It's of degree 2. So this is a plane curve. So Z1 and Z2 are coordinates in C2, but we need to think of this in P2. And what we're looking at here are, okay, these are conics in P2, which have the property that they actually pass through 2 points at infinity. And so there's a 5-dimensional space of conics in P2, passing through 2 points gives us 3 dimensions. We could do that, we could blow up those 2 points and blow down the line joining them, and that will give us a quadric surface, and then these would be the plane sections of the quadric surface. So that's basically the quotient there is, this is a case where we don't get a nodal curve, the curve is smooth, it's this smooth conic, and we're getting the Einstein-Val manifold, which is hyperbolic space of anyway, constant curvature, constant non-zero curvature. On the other hand, if we go one stage up and we eliminate lambda in the next one, then we get something which is a degree 4. So it's a plane quartic curve. Again, it passes through 2 points at infinity, but But there are many, many more such curves like that. So, well, of course, it's got to have singularities as well. It's got to have nodes, but the numbers basically don't add up. And more generally, what you're going to get is a curve, a plane curve of degree 2n plus 2, which has, okay, the standard formula gives you this as its genus. And there's no way in which this can satisfy those constraints of Honda in order to get an Einstein-Weil manifold. So somehow this, although we're getting this kind of projection onto the plane in this particular case, gives us some nodal curves. The images of twistor lines are nodal curves. It's not, if you like, they fill out a much bigger space. I mean, there's a much higher dimensional space than what we're expecting in order to get a three-dimensional Einstein-Weil manifold. But these are special. These are rather special. So they are, okay, so if we have a root of unity, e to the 2 pi I over 2n plus 1, then actually these curves, this is the parameterized version of the curve, you see that it's invariant under this action. If you like, if you look at the quartic there, you'll see that actually if you multiply z1 by a cube root of unity and z2 by its inverse, then this is invariant under that action. So we can do something. So more generally, what I can say is that this curve is of degree 2n plus 2, and it's invariant under this action of a cyclic group of order 2n plus 1. Now, it was given by a polynomial, and we know that a basis for the invariant polynomials under this action, we know from Klein very well what they are. So x, y, and z, they satisfy a relation. X, y equals z to the, in this case, 2n plus 1. But in particular, if we look at the, if we look at the, okay, if we look at the formula, what we've got is we've got polynomials in z1, z2, and z1, z2, and we can substitute in that to get something which looks like this. So if we take the quotient of C2, or P2, I should say, by this cyclic group, then of course we're getting a singular space, but this is the way in which we're actually going to get a three-dimensional space of solutions. So well, you can do some counting of coefficients, or you can use Riemann-Hurwitz just to see what you're going to get. So in this case, what we're going to get is that there is a mini twistor space which has nodal twistor lines. That mini twistor space is the, if you want a smooth one, it's the resolution of the singularities of P2 modulo this cyclic group. And this is a compactification of x, y equals z2n plus 1, the basic equation linking those three invariant polynomials. So, in fact, you can see what the nodal curves are going to be, because we're looking at an equation right at the top, which looks like this. But if we multiply it by y and use the equation xy equals z to the 2n plus 1, you get something which is a quadratic expression in y, whose coefficients are polynomials in z, so it's of this form. And so if this were a smooth curve, we would say that this was a hyperelliptic curve, branched over P1 with 2n plus 2 branch points. So you see that C1 squared is a degree 2n plus 2. So if we want to get a nodal one, then we need to restrict C1 and C2 to have n double zeros. So this is a very concrete example of a surface, an algebraic surface, which has nodal curves which describe an Einstein-Weil manifold. Now, actually, finding such nodal curves in this case is relatively straightforward. but in general, of course, it's not. So I'm not saying that this is an easy route to finding Einstein-Weil manifolds, and in fact, in this particular case, it's pointless trying to do it that way because Paul and Wiedersehn, and I think it appears in a number of other papers, they actually write down explicitly the Einstein-Weil manifold here. So it's written in this. This is the way in which it's more convenient to do it. There's a particular metric in the conformal equivalence class, and there's a one-form omega, which is basically the connection form on the volume form. And anyway, this is this. Now, what they say in the paper is that this metric has conical singularities at theta equals 0 of pi, and that we can see through this quotient action because the C star action has isotropic groups, different isotropic groups on Z2 equals 0 and Z1 equals 0, which are these two surfaces inside. So anyway, so that was okay. So later on, maybe I'll mention a reason for actually carrying out this exercise, but at least it starts out by giving you a concrete example of the way in which you can understand some three-dimensional Einstein-Weil manifolds as quotients of some well-defined complex manifolds by a C-star action, where the twistor lines become nodal curves. Okay, so now let me go switch over to ALE spaces. So a priori, I'm not thinking about nodal curves here. I'm thinking about how do we construct hyperkähler metrics on ALE spaces by twistor method. So let me recall for you what an ALE space is. That we take a finite subgroup of SU2, take the quotient by C2, the quotient of C2 by gamma. We resolve that singularity at the origin, and you get a complex surface with a configuration of smooth irrational curves, which fit together according to the Linkin diagram of type ADE. And the group gamma, of course, is at least the image in SO3 is either cyclic. So these correspond to cyclic, dihedral, tetrahedral, octahedral, or icosahedral groups. And here's an example. This is 1, 2, 3, 4, 5, 6. This is E7. Okay, so, I mean, there is a construction. I mean, a very beautiful construction by Kronheimer of these metrics. So you might say, what's wrong with that? And there's nothing wrong with it. It's just that it's a hyperkähler quotient construction. And of course, we also know how to understand hyperkähler quotients in twistor theoretic terms. And so implicit in this, in its construction, is some twistor theoretic description. The only thing is that the quotient, if you take E8, for example, then the space, the vector space, which you have to take the quotient of, well, anyway, in general, it's a vector space, a real vector space of dimension 4 times the order of the group. So it's a very, very large vector space. And you're going to look at an action of a very, very large group on it and take the quotient until you get finally down to a four-dimensional manifold. So, on the other hand, his construction is very beautiful, and it gives you all the things you want in terms of completeness, smoothness, moduli, and so on and so forth. But nevertheless, there's been a kind of niggling feeling that maybe one can get closer to the metric by using twistor theoretic methods. So the first thing you will need to do in order to do that is to construct the twistor space. So just if you're given the twistor space, it's usually a much harder problem to find the twistor lines. So in this case, the twistor space is well, we've known about this for a long, long time. So again, it's the same story as I just talked about for the cyclic group. And there are invariant polynomials of certain degrees, three of them, basically three basic ones which satisfy a single equation, which gives the quotient as a singular surface embedded in C3. And this singularity has a versal deformation, which involves adding on lower degree polynomials. And the coefficients of these lower degree polynomials have to be invariant polynomials in the Cartan subalgebra, invariant under the Weil group. And so then you get a function f of x, y, z depending on these parameters h1 up to hk. And Cronheimer's hyperkähler moment map is this is the way you do it. You take a vector space, which is the L2, the regular representation L2 of the group. You look at the endomorphisms of that, tensor it with C2. That's a hyperkähler. Sorry, it is hyperkähler. It's a quaternionic vector space, so then in a product on it. You look at the gamma invariant part of that, and then you have a moment map, a hyperkähler moment map for that under the action of the group G, which is the gamma invariant part of the unitary group of this regular representation. Anyway, the point is that there's a choice of moment map which depends on something in H, in the center of H, of G. And so in twistor theoretic terms, we interpret R3 as being the holomorphic sections of O2 on P1, and then choosing a value for the moment map is choosing some polynomials, quadratic polynomials like this. And then the twistor space is basically given by looking at this equation in 4 variables. So x lives in OL, y in OM, z in ON. And then, okay, for certain values of u, you're going to get a singular, in general, you get a singular surface, and you need to resolve that to the singularity simply. And here are the two most obvious situations. The AK twistor space basically has this equation, and the DK twistor space has this one. If you want to think about the coefficients in terms of invariant polynomials, then you can think of these things as being, so you think of dk as being associated to SO2k, whatever it is. Anyway, the even dimensional orthogonal group, these are like Pontryagin classes, this is like the Euler class, and these are like Chern classes for SUN. So then if you want to do it that way, then you say that, okay, the twistor lines are going to be sections of this. So this has a fibration over P1, the parameter U. And finding the twistor lines this way involves looking at polynomials x, y, and z of appropriate degrees, which satisfy this equation. And that is, so this is like if you approach it this way, then this is like trying to solve a Diophantine equation. You've got it, instead of having like a polynomial with integer coefficients, trying to solve it with integers, this is a polynomial with polynomial coefficients, you're trying to solve it with polynomials. And it's difficult. So, but I managed to do it, so back in 1979, I managed to do it in the case of the AK case and the DK case that we just, so I should basically explain this. So this was a long time ago, right, 1979. And this paper, as you see, is 2005. So why the long delay? Well, basically, for the first paper, we already had a very nice formula for these metrics given by Gibbons and Hawking. You could see explicitly what the manifold was. You could see that it was asymptotically Euclidean, smooth, everything possible. So what this paper that I wrote did was to actually give a twistor interpretation of a pre-existing metric. It also, at the same time, actually told you what the complex structures were in terms of algebraic equations. In this case, I found solutions which involved an elliptic curve which satisfied some constraints. So this was a double covering of P1 branched over 4 points, but there was a single constraint on it. And I had although I gave a formula, quite a complicated formula, there was nothing to compare it to. And the formula wasn't sufficient to say that this is asymptotically locally Euclidean, this is smooth, this is complete, anything like that. So it was just a formula. And so it kind of sat on the back burner for years and years and years until Cherkis and Kavustin started looking at moduli spaces of monopoles, in particular charge 2 monopoles with singularities. And then, for those who know about this, a monopole, an SU2 monopole, has a spectral curve. And it turned out that the spectral curve was an elliptic curve for charge 2, and it satisfied more or less the same constraint that I was using. Actually, that's the monopole moduli space was the ALF version of the DK rather than the ALE version. So then, Cherkis's instigation, we wrote a paper where this formula appears. But it was a situation where we knew that there was an existing hyperkähler metric. The Twistor construction said that actually these curves and their deformations are the ones that give it, and therefore this complicated formula is the right one. So that explains how many years there are between 2005 and 1979. Anyway, even back then, I thought, what can I do next? And of course, the next thing is to look at E6, E7, and E8. And then the corresponding equations are not so bad, I suppose. Here we have these surface. Sorry, these are the versal deformations of the corresponding singularity. And these coefficients, as I say, are polynomials are invariant polynomials in the Cartan subalgebra of E6, E7, and E8. And this paper by Katz and Morrison actually, well, they don't do E8, but they certainly do E6. And so, this is not going to work. If we try and write down the equation as before, try and find polynomial solutions, well, it's just not going to work. So I kept thinking, well, is there some way in which we can attack this in a different way and get some more information about the ALE metric? In order to do that, so I thought, well, let's try and look at a special case, possibly the most interesting case, where we look at the circle action on C2, just scalar multiplication by e to the I theta. And then most of the Dynkin diagrams have a trivalent vertex here. And so that resolution, that copy of P1, that has to be pointwise fixed by this circle action, because there's no way in which you can get a two-sphere with a circle action with 3 points. And so this basic central sphere here was something which attracted my attention. So in particular, I thought, well, suppose we could try and solve these equations somehow in Twistor theoretic terms for this class of ALE spaces which have the circle action. Okay, so on the real manifold there's a circle action. That means that you actually have a particular type of, you restrict the choice of the hyperkähler moment map, but otherwise it's more or less the same. Then the circle action acts on the Twistor space, and this is the way that the sort of complex structure I, which is the complex structure of the resolution, is preserved, but the other ones are rotated. So, and in fact, in this situation, it makes a lot of sense to restrict in the AK case to the odd ones, because then the Dynkin diagram does have a central one, and also because -1 is then in the group gamma, which means that actually we can consider this circle action on the quotient in the quotient as being just e to the I theta instead of e to the 2I theta. And so in this case, the fixed points are where we have this central P1, which is pointwise fixed, and the other fixed points of the circle action are the pairs of points on the other two spheres. And then if you look at the action on the tangent space at each fixed point, well, you'll see now here why I was interested in those examples of flat space as a kind of model for what's happening at the other fixed points. So here we have a trivial action that's on the tangent space of the central 2 sphere. This is actually in the normal direction. That's also an action on the next 2 sphere which hits it. And then the opposite pole, it's e to the minus I theta, then it has to be e to the 2 I theta because the action on the symplectic form is e to the I theta, etc., etc. Okay, so in this case, so we can try and with this kind of C star action, we can try the slice approach again, the compactification. In this case, we do have a compactification. So in fact, each of these fibers in the twistor space has a natural compactification by a configuration of projective lines. So the numbers here are the self-intersection numbers. So we have an exceptional curve C of self-intersection -1, and then we have these EFGs which come off this. So this is the compactification for the EK series. And those 3 points, so basically what you're looking at is CP2, P2, modulo the group gamma, and then you have the line at infinity is C, but there are 3 orbifold points on that corresponding to stabilizers of vertices, edges, and faces. And then those need to be resolved in order to get this configuration. So this is a standard part of studying these singularities. And in particular, this configuration of curves supports an anti-canonical divisor. And so what we could say is that in the complement, we have this holomorphic 2 form, and it acquires poles on C, E, F, and G. So it has a double pole, if you like, along C, and then simple poles along E, F, and G. And the compactification is a rational surface, and we know how to construct rational surfaces. It's either a Hirzebruch surface, or it's obtained from P2 by being blown up at a certain number of points. So instead of looking at an equation, the previous approach was looking at the equation and trying to solve it with polynomials. Here we can try and construct these fibers in the twistor space by resolution. So the fiber over u equals 1 before the compactification is an affine surface. This has a natural holomorphic 2 form on it. This is the 2 form which has those poles at infinity. And now we're going to do what we said before. We're going to kind of project the twistor lines onto this to get some nodal curves. So here, for example, this is the way you can construct the fiber for E8. So you take a conic in the plane, and that's the green conic E. You blow up a number of points here, and now we've got our E, F, and G. So what you see here is that you see the line G is a tangent to E at F. So when you blow up F, then you'll get 3 curves meeting at a point. But if you blow it up again, then you'll get a -1 curve, and you'll get the E, F, and G meeting it in E, F, and G like this. So you have to do, if you like, an extra blow up. So, but all the parameters are there somehow. The choice of the positions of the lambdas, if you like, in the formula are there in terms of choosing the positions of these points. Anyway, so what are we going to do? We're going to look for a twistor line in the actual compactified twistor space, and we're going to look at the closure of a C-star orbit of that. This will be a compact surface, and it will intersect the compactification of the fiber over u equals 1 in some curve. And that curve will be our nodal curve. It'll be, if you like, the projection of that twistor line. Then the most obvious problem is, well, can we find the cohomology class of this curve? After that, this is a rational surface. The linear equivalence class, the equivalence as a divisor, is determined by its cohomology class. And so the family of curves which it lies in will lie in a particular divisor class, which is equivalent to the cohomology class. And then the cohomology class of the fiber, well, of course, the cohomology of the fiber is the isomorphic to the cohomology of any of the fibers. If we remove the point of the divisor to infinity, we know that it's from a C infinity point of view. Actually, this is just the product of S2 across the full manifold. But anyway, the fibers are actually isomorphic cohomology. So, and what we know then about the cohomology of the fiber over 0 is that we've got these P1s in the resolution. We've got these P1s at infinity, C, E, F, and G. So the idea is to try and see what the cohomology class of this intersection, this C star closure of the C star orbit is. So first of all, it's perhaps useful to think just of the fiber over 0. And you can think of this in lots of different ways in terms of the stratification under the action of the C star orbit. We can also think in this case of the gradient flow of the moment map. So we have this on the inverse image of 0 on this surface here. This is the resolution of the singularity. And we have an S1 invariant Kähler form, so a moment map for that. And the absolute minimum of that moment map is this fixed two-sphere. I've called it C0. This is the pointwise fixed two-sphere. Then you can look at the downward gradient flow under this. That's part of the C star action. And this has limits which are fixed points. And a generic one, a generic orbit, is going to go all the way down to the minimum. And so what we know is that in this fiber, a generic point, a generic intersection with one of these twistor lines, does go down to C0. And so, on the other hand, a generic one is not going to intersect. It's not going to hit the other levels. There'll be some. This is this is what's called the Morse complex. You're looking at some of the flows. The downward flows will hit some of their fixed points and then go down again. But a generic one, big open set, everything goes down to C0. So the generic ones won't intersect any other of the points in this, any other P1s in this resolution. Okay, and the upward flow, we can look at, instead of looking at the downward flow, the upward flow has a limit on that curve at infinity, that's C in that configuration. And similarly, a generic orbit only intersects that in points which are not points not on E, F, and G. So this in this fiber, we can see that there are. We take a point of intersection, the twistor line in this particular fiber, then that orbit only meets the point at the curve at infinity in one point, and the curve at C0 at one point. But now if we look at the downward flow in the whole twistor space, if we look at the C star action on this, then there's again an open stratum where a generic orbit has a limit on this C0. The downward flow takes you to C0. So in fact, the closure of any orbit of a generic twistor line intersects C0. Now, if you look at the flat case of C2, then we've done this before. We eliminate this, and we get this. Eliminate lambda, we get this closure of the orbit here, and this intersects the fiber at u equals 0 in two orbits. Actually, so previously I was saying we look at where the twistor line hits that fiber, and we look at the orbit of that. But in the closure of the twistor line, the orbit of the twistor line in the full twistor space, there's another orbit as well. So what we get is that we get two C star orbits, and we get C0. So that's in the flat model, but when we take the quotient by the group gamma, then we're going to get the same kind of picture. So the upshot of this is this: that we have this this surface X, this closure of the C star orbit of a generic twistor line. Its intersection with this curve at infinity is equal to 2. Its intersection with C0, well, it's got to be greater than or equal to 0. But in fact, C0 at u equals 0 and C0 at u equals infinity are the same two spheres, but they have opposite complex structure. Complex structure is I and minus I. And so it has to intersect that in a negative degree, less than or equal to 0, and so the result is that it has to intersect it in intersection number is 0. It physically intersects it, but the intersection number is equal to 0. And so this then determines the cohomology class. That we're looking at a cohomology class which intersects the curve at infinity in 2 points and has intersection number 0 with C0. And so, well, you can just do that. So you can, this is what you find. So I called it Q now, this divisor class. So for E6, E7, and E8, and the divisor classes involves C and the E, F, and G. So it's supported, well, this is a particular divisor which is supported at infinity, but of course, as you deform it, then you get curves, other curves. And so what we get then are, so these C, E, F, and G are smooth rational curves. So you can use the junction formula, and you'll see that, so you can work out, you've got the self-intersection numbers from the diagram, you work out what Kc is for this Q, and you find that in all cases it's equal to -4. So now we can appeal to Honda and Nakata, who say that actually now, because we've got this condition, the actual deformation space of these nodal rational curves are actually is actually three-dimensional. On the other hand, we have this four-dimensional family in the twistor space, and the quotient by C star is going to give us a three-dimensional family. So these, generically, these rational curves are the ones which we get from the projections of twistor lines. Okay, so now, I missed out the AK case and the DK, but there's a slightly different configuration. Here, the Hertzsprung surface looks like it's really a projective bundle over P1. You blow up some points. The parameters, you blow up on the D2, and you get that configuration. And you get a similar picture from what we had actually in the flat quotient situation, but now you've got some parameters in it. So the flat case was some kind of degeneration of this, where all the parameters in this metric, this AK metric, go to 0. So again, the nodal condition is again this. Okay, so when I started doing this, I wasn't specifically interested in thinking of what the quotient Einstein-Weil manifold would be. On the other hand, Honda's approach, was largely motivated by mini twistor spaces and Einstein-Weil geometry. So there are obvious questions that we start with an ALE space, and we take its quotient by S1, and we get a singular Einstein-Weil manifold. And you can ask, well, what happens near the fixed sphere, S0? That's where we, if you like, the action is going to look like this, and we can use the flat model that we worked out to say that actually this is like hyperbolic space. Okay, so actually, because as we know, in particular from work of Itera on magnetic monopoles, that the mini twistor space for hyperbolic space is the quadric. So what we can deduce from this is basically that sphere, that central sphere in that 4 manifold, becomes, if you like, the 2 sphere, which is a kind of boundary at infinity in the Einstein-Weil space. So you could call this, Poincare Einstein is where we have Einstein metrics which blow up rather like hyperbolic space. So you could call this a Poincare Einstein-Weil structure. And on the other hand, the infinity, so this was the C0, this is right in the center of the resolution. So that becomes the infinity in the Einstein-Weil manifold, and infinity in ALE space becomes a finite point in the Einstein-Weil manifold, but it's an orbifold point. So it has the structure of R3 modulo the action of gamma. But what happens in between is, of course, the other fixed points of this type. And then I've already kind of discussed earlier the kind of model, the flat model. And so the singularity of the model is quite complicated. So I think in terms of the geometry of these quotients, these Einstein-Weil quotients, I think it's a bit difficult to actually do anything very seriously with them. Except for this, so in the case of A1, which is the Iguchi-Hansen metric, and then this is where we have the quotient is non-singular, and it is actually, well, the mini twistor space is the quadric surface, and the quotient is hyperbolic space. And you can see, okay, this appears in a number of places, seeing that hyperbolic space is a quotient actually of not just of S4, but also of the Iguchi-Hansen metric. So, the last 2 minutes, let me say that there's one feature about Einstein-Weil geometry which makes sense of something which at first was rather puzzling to me. So if we look at I've been doing everything so far over the complex numbers. If we put in the real structure, then in the original mini twistor space picture, our complex surface was supposed to be the space of oriented geodesics in the Einstein-Weil manifold. And the fact that 2 such curves meet in 2 points, self-intersection 2, is equivalent to saying that given only 2 points, there are 2 geodesics with the orientations joining them. So one thing you get, if you just work out this self-intersection of Q with itself, you get a number which is always the order of the group gamma. And at first I thought that's a curious feature. So remember, this was determined by the cohomology condition that it's intersected. The intersection number with C0 is 0, intersection number with C is equal to 2. And so is there an explanation of this? And there is an explanation in terms of Einstein-Weil geometry and their geodesics, because you see, what it means is essentially that there should be this number of oriented geodesics between 2 generic points. On the other hand, you see, if we look at the orbifold point, which is like R3 modulo gamma over plus minus 1, then if we have a fundamental domain for that action, then we could look at a geodesic for 2 points in that fundamental domain, But then you can hit it with an element of the group and another element. You can just hit it with any element of the group, and this is the way you get your gamma, order of gamma number of geodesics. So the Einstein-Val interpretation is a kind of an explanation, in some sense, of this algebraic fact that this self-intersection number, in this case, is equal to this. So that, okay, is maybe a point at which I can stop.
Questions? So there was a very nice approach to the twistor spaces of the DK and EK gravitational instantons that came out of some of Roger Bielowski's work, where instead of having a map to, rather than the twistor space mapping to the O of 2 line bundle over CP1, it could map to the O4, O6, and so forth. And I wonder if there's a direct way. So there's actually a projection. I'm a little bit puzzled actually in how the Einstein-Val picture fits into this when you don't actually have an honest-to-goodness C-star action. But in this case, there was a projection, and I wonder if you can fit these pictures together.
I think the point is, what do you choose? So, for the DK case, there's a projection to O4, which is choosing what I call Z in the formula. So Z is then a quartic polynomial. So instead of x, y, z as being, anyway, Z is a quartic polynomial. And that is the polynomial whose zeros define the branch points of the elliptic curve, and there's a single constraint. So the quartic polynomial has 5 coefficients. There's one constraint on that, which in this case was realized by periods of integrals, basically. So for E6, E7, E8, you've got these x, y, z, each one you can project any one of these, you've got 2, 3, 5, or whatever. But then the number of coefficients is bigger, and therefore the number of constraints is, in order to get a four-dimensional family, is bigger. And I felt that it was also, you have to choose. Why choose X instead of Y, or Y instead of Z? And maybe there's some reason for it, because you can all define these as some kind of conic bundles, and maybe, but I think that's the reason that I didn't think that was necessarily a proper approach. Maybe for, E6, I can't remember what the degree is now, but it was difficult enough with DK to impose a single constraint on 5 coefficients, than imposing many more constraints on the coefficients, and also the question of why make the choice? Why make the choice of X, Y, or Z? So better to anyway. Yeah, this is another way of looking at it.
I mean, so these are S1 invariant A and E spaces. How big are the moduli spaces when you cut down from AK to
Well, it's
really...
really...
AK is just N or K minus 1 points on a line or something, isn't it?
Yeah.
But what is it for DK and the E's?
Well, it's basically these real coefficients for so the hyperkähler moment map is now going to be real. So if you like, the polynomials that you put in are actually all scalar multiples of what I call U.
I see. So
the
it goes down
parameters
by a third or something.
Yeah, that's right.
Oh,
Yeah.
I see.
So
Nice.
you just have
Okay.
these real numbers. And what that means is that it's also a little bit easier to determine the non-singularity conditions, because before you got to keep away from the walls of the chamber, the Val chamber, and somehow when it's all in one line, I think it's a bit easier. But yeah, but that's all it is.
I see.
You're just
That's
cutting
very
down
nice.
the coefficients.
Okay. If there are no other questions, let's thank Nigel again for being here.